Chapter 3, Internal Energy and Enthalpy. Section 3.6, Enthalpy of Reaction and Enthalpy of Formation. Hess's law states that regardless of the steps in a reaction mechanism, the total enthalpy change for the reaction is going to be the sum of all changes involved in all steps. This is only because enthalpy is a state function. Therefore, the enthalpy change of a chemical system is going to be the enthalpy of the products minus the enthalpy of the reactants, regardless of the steps involved in this reaction mechanism. For example, we can determine the enthalpy of reaction for this reaction from A to 3D plus E given the information about three individual reaction steps. Over here we have the reaction from A to 2B plus C, from D to B, from D plus E to C. So now let's look at these three reaction steps. We see A appears only in the first reaction step. Therefore, we need this reaction step, so we put it here. And also, in this target chemical reaction, we do not see any B or C. So somehow we need to cancel this 2B. Therefore, we use this reaction from D to B. We change its direction. It becomes from B to D, and then we multiply that by 2, and that's why we multiply 30 by negative 2 here. And also we need to cancel this C. Therefore, we need to reverse the third reaction step so that C appears on the left hand side, and we need to change the sign correspondingly from negative 10 to positive 10 here. Now if we add up the left hand side, it's A plus 2B plus C on the left hand side. We add up the right hand side, 2B plus C plus 2D plus D plus E. And now the total enthalpy of reaction is going to be 20 minus 60 plus 10. The result is negative 30 kilojoule per mole. And if we look at this chemical equation, we have 2B on the left and the right. We have C on the left and right. We can combine this two. Therefore, we get A to 3D plus E. The enthalpy of reaction is negative 30 kilojoule per mole. Now let's look at another example, problem 3.6.1. Calculate the enthalpy of reaction. This is from A plus 2E to 3C using the data provided in the previous example over here. So we have this from A to 3D plus E. We copy this here, and then somehow we need to get rid of the D's, and we need to introduce C's into this equation. So we have this 3D plus 3E equals 3C. That's negative 30. That's from this reaction step multiplied by 3. And then we combine this two. On the left we have A plus 3D plus 3E. On the right we have 3D plus E plus 3C. The left and right cancel. Well, the 3D on the left and the 3D on the right cancel. And over here partially cancel. And then we have this final equation, A plus 2E, we get 3C. And the enthalpy of reaction is simply negative 30 minus 30, it's negative 60. Because enthalpy is a relative quantity, the value of H, the enthalpy, can be determined only after some zero references are defined. The UPAC decided that pure elements in the most stable state of aggregation, it could be solid, liquid, or gas, under the standard pressure, which is 1 bar, they have a zero enthalpy of formation. It's written this way: standard enthalpy of formation is 0 at 298.15 Kelvin. That's the room temperature. Over here, this delta actually denotes change. So what kind of change? Well, it's changing from the pure elements to compounds, and we need this data. What if the change is from pure elements to pure elements? Well, that's just 0. That's why, the enthalpy of formation of pure elements in their most stable state of aggregation under the standard pressure at room temperature is simply 0. Note that the room temperature is used in the definition of the enthalpy of formation, not the standard temperature. The standard temperature is actually 0 degrees Celsius. the room temperature is 25 degrees Celsius. The UPAC has chosen this room temperature in the definition of the standard enthalpy of formation. Again, the standard enthalpy of formation of a compound is the enthalpy change of the formation reaction in which the product is the compound and the reactants are the pure elements in their most stable state of aggregation, each in their standard state at room temperature. For example, the standard enthalpy of formation of propane, carbon 3, hydrogen 8 is the enthalpy of the reaction of this. From 3 carbon and 4 H2 we get propane, because on the left hand side graphite is an element and this hydrogen gas is an element. Okay, and remember, when we define the standard enthalpy of formation to be 0 for pure elements, the temperature has to be room temperature. So we have 298.15 Kelvin for the temperature. And also, graphite, not diamond, is the most stable state of aggregation of carbon under 1 bar pressure at room temperature. Under this condition, graphite is slightly more stable than diamond. And in the above standard reaction of formation of propane over here, H2 and propane are both gases. They're in the gas phase, and to make sure they are under the standard condition, they have to have a standard 1 bar pressure. How about graphite? It's a solid. So for a solid in the standard state, that solid has to be under 1 bar external pressure. Same for the liquid. If we say a liquid is in the standard state, that means that liquid is under 1 bar pressure. The standard state of reaction is almost always hypothetical. This is just because for all 3 chemicals in the reaction to be in the standard state, you have to have a 1 bar propane, 1 bar H2, and also at the same time the graphite is under 1 bar external pressure. It's almost never achieved. Now if you look at this notation, delta U superscript naught is delta U with all involved chemicals in their standard state. This superscript 0 or superscript naught means standard state. Same here, in delta H superscript naught, it means delta H when all involved chemicals are in their standard state. Again, this superscript naught in delta U naught and delta H naught denotes the standard state, and this indicates every single chemical involved in the chemical reaction is in the standard state. The standard state is also defined by UPAC. If you click this web link, you can get to the definition of the standard state. The standard state is the state of a system chosen to be the standard for reference by convention, and the following standard states are recognized. For a gas phase, it's the hypothetical state of the pure substance in the gaseous phase with P is equal to 1 bar, and assuming this gas behaves ideally. So that's why it's hypothetical. None of the real gases is really ideal. For a pure phase or a mixture or solvent in a liquid or in a solid, it's the state of the pure substance in the liquid or solid phase at the standard pressure. P is equal to P naught. So if you have pure gold under the standard state, it has to fill 1 bar external pressure. And if you have pure mercury in the standard state, that means the mercury is under 1 bar external pressure. For the solute in a solution, the standard state is also the hypothetical state of solute at this concentration. Well, you can say 1 mole per kilogram solvent or 1 mole per liter solution. So which one is correct? Well, it really depends on the situation, how the properties of this chemical in the standard state is tabulated. But they should be under the standard pressure, which is 1 bar pressure. And also over here, very important, this is hypothetical because the solute has to exhibit infinitely dilute solution behavior. So that's why it's hypothetical. For the solvent in a solution, its standard state is when the mole fraction of this solvent is 1. Actually, that means pure solvent, so it's also a hypothetical state. For alloy, the standard state of each metal is when its mole fraction is 1. That means pure metal. So we can never reach the standard state if you have an alloy. But you can imagine there are two different metals forming this alloy, and if one of the metals has a mole fraction of 0.9999, and approximately this metal is in the standard state if it's under 1 bar pressure. The standard state is defined so that zero references are available for relative quantities such as enthalpy and some other thermodynamic properties. Now we have a bunch of equations for the internal energy of reaction and enthalpy of reaction. For example, the internal energy of reaction is simply the internal energy of products minus the internal energy of the reactants. And specifically, if all chemicals are in the standard state, we can put a superscript naught for this internal energy of reaction and also for the internal energy of products and that of the reactants. Same for enthalpy. If you look at this, it simply tells you the enthalpy of reaction is equal to the enthalpy of products minus the enthalpy of reactants. And again, we can specifically put a superscript naught here for all three terms. So this means the standard enthalpy of reaction is the enthalpy of products in the standard state minus the enthalpy of reactants in the standard state. Again, there's no way to determine the absolute value of enthalpy for any chemical because enthalpy is a relative quantity, and therefore we often define zero references. The enthalpy of formation of pure elements in their most stable state, if the pure element is also in the standard state at room temperature, and we say they have a zero enthalpy of formation. So pure elements are simply chosen to be the zero references. And then it's easy to compute the enthalpy of reaction. So over here we have the standard enthalpy of reaction. It's simply the standard enthalpy of formation of the products minus the standard enthalpy of formation of the reactants. It's easy to determine experimentally the change of H or U of the reaction because we can simply measure the reaction heat. Delta H of a reaction is equal to the reaction heat at constant temperature and pressure condition. The internal energy of reaction is equal to the reaction heat at constant temperature and volume condition. So we'll have to pay attention to the experimental conditions. Constant Tp, Q is delta H. Constant Tv, Q is delta U. For safety and lower cost, most chemical reactions are conducted under the isobaric condition. That's why we often deal with the enthalpy of reaction instead of the internal energy of the reaction.